Hello there, and welcome back to the Science Sleepy Minds, where your dreams flirt with particle decay and your nightmares probably violate general relativity. Tonight, you're floating at the rim of a place that doesn't play by the rules. It's vast, it's invisible, and it's been quietly rewriting the laws of the universe since before you were born. Above you, space stretches like taffy, stars warping into spectral smears. Below you, an endless void pulling not just on your body, but on logic itself. You've arrived at the event horizon, the boundary of a black hole, and tonight, we're not just going to dip a toe in, we're swan diving into one of the most unsettling puzzles in theoretical physics, the Firewall Paradox. Spoiler, you probably won't survive this. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, post your location and local time in the comments, because if you're about to fall into a black hole, it's nice to know where you started. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You drift near the edge of a black hole, light from distant stars circling the abyss like moths around a drain. No sound, no wind, just a tug. A quiet, persistent invitation from gravity's final form. You float here, frozen in time to a faraway observer, but to you everything feels normal, strangely calm. No flaming death yet, no explosive radiation, just you, silence, and the darkness curling toward you like a lazy tide. But this calm, it's lying to you. Physicists used to think you'd fall in painlessly. That's the so-called no-drama scenario from Einstein's general relativity. Cross the event horizon and nothing special happens until you're utterly crushed inside. Lovely. But recent ideas suggest that calm might be a trick. You might slam into a wall of searing energy the instant you touch the horizon. A firewall so intense it would incinerate you before you even knew you'd arrived. According to some equations, the smooth, empty space you see is a lie, and that's the paradox we're here for. Firewalls shouldn't exist, but apparently, maybe they do. You're not alone in the confusion. Even seasoned physicists admit this puzzle keeps them up at night. Thinkers like Stephen Hawking, Leonard Susskind, and Juan Maldacena have all tried to tangle with the contradictions here. Some argue it's the most important question in theoretical physics, others think it's just a mathematical misunderstanding, and then there are those quietly hoping we just don't talk about it anymore. Too bad, we're talking about it. Imagine this, you toss a book into a black hole, not just any book, your teenage diary, let's say. It vanishes past the horizon, taking all its secrets with it. But quantum mechanics tells us that information, the contents of your diary, the molecules that made it up, the awkward crush confessions inside, can never truly be destroyed. It can be scrambled, hidden, but not erased. Ever. So where did your diary go? For decades, that question haunted Hawking. In the 1970s, he proposed that black holes aren't perfectly black. They emit faint radiation due to quantum effects near the event horizon. This is now called Hawking radiation. Over time, this process causes black holes to slowly shrink and eventually evaporate completely. And that's where the real trouble starts. If the black hole disappears, and the radiation it emitted carries no trace of the diary's contents, then the information is gone. That breaks the most sacred rule of quantum theory, unitarity. Basically, in quantum mechanics, the total information in a closed system must always be preserved. The universe doesn't forget. But Hawking's model said black holes do. That contradiction, the tension between general relativity, which describes gravity and the smooth curvature of space, and quantum mechanics, which governs particles and information, has sparked 50 years of confusion, retractions, and increasingly wild theories. It's like watching two brilliant but stubborn roommates argue over how to clean a shared kitchen. One uses a mop, the other uses probability waves. Now, here's where things start to really twist. To fix the paradox, some physicists began exploring what happens at the event horizon when the black hole radiates. They found that if Hawking radiation is entangled with the stuff inside the black hole, which it must be to preserve information, then eventually that creates a kind of contradiction. You can't keep all those quantum relationships consistent without breaking one of three things. 1. The idea that information escapes in Hawking radiation, which we now suspect it does. The notion that space is smooth and empty at the event horizon, which general relativity demands, or the rule that quantum entanglement can't be duplicated or broken willy-nilly. You get to pick two, but not all three. Choose wisely. That's where the firewall enters. To save unitarity in quantum entanglement, some theorists propose that the second option must go. That means, instead of crossing the event horizon without noticing, you'd smash into a wall of high-energy particles, the firewall. This would violate general relativity's prediction, but it keeps quantum theory happy. Just imagine. A boundary that appears perfectly calm and silent, but the moment you touch it, boom, you're vaporized by a quantum inferno. Sounds like a great place for a vacation. The original proposal came in 2012 from 4 physicists, Almhiri, Marolf, Polchinski and Sully, now affectionately known as AMPS. Their paper was short, dense and devastating. It argued that something had to give, that we couldn't keep pretending everything was fine at the event horizon. Their solution? Burn it all. Now, historians still argue whether the AMPS paper truly demolished the no-drama principle, or just exposed a conceptual blind spot. Some claim firewalls are inevitable, others think they're unphysical, like dividing by 0 in the wrong dimension. But the damage was done. The firewall debate had entered the physics canon, and here you are, drifting closer to the horizon, wondering, is there really a wall of flame waiting for you? Or is it just a ghost born from math too complex for human brains to tame? Fun tidbit. Early models of black holes suggested they were completely black, letting no information or energy escape. But in 1974, Hawking used a trick from quantum field theory near curved spacetime to show that virtual particle pairs could create a tiny imbalance at the horizon, letting one escape as radiation. It wasn't just genius, it was accidental genius. Hawking apparently didn't even believe the result at first. And then there's this fringe notion, popular in the back corners of conferences and conspiracy-adjacent physics forums, that firewalls aren't real but necessary illusions, like safety rails in a simulation. Yep. There are actual discussions about whether black hole paradoxes prove we live inside a giant cosmic rendering engine. Insert please unplug me jokes here. But simulation theory aside, the key takeaway is this. Physics has rules. Black holes appear to break them. And firewalls? They're a desperate attempt to tape the rules back together using logic, duct tape, and just a little bit of terror. You inch even closer to the horizon now. Still no heat. Still no bang. The stars are redshifting into nothing. Time itself stretching like taffy. Are you moments away from vaporization, or about to slip in painlessly just as Einstein promised? You're about to find out. You fall. There's no sound, no resistance, just a slow, syrupy surrender to gravity. Time warps around you. If someone were watching from far away, they'd see you freeze near the event horizon forever, like a paused hologram. But to you, falling feels smooth, continuous, a little eerie but not especially dramatic, which is weird because you're now spiraling toward the most extreme object in the known universe, a black hole. So what exactly is a black hole? It begins life in violence. Somewhere, long ago, a massive star burned through its fuel and collapsed under its own weight. Normally stars keep themselves puffed, up by fusing elements in their core, hydrogen into helium, then heavier and heavier stuff like carbon, oxygen and iron. But once it hits iron, game over. Fusion can't continue. Gravity wins. The star implodes. If it's massive enough, even the dense, neutron-rich core collapses, compressing all that mass into a point of infinite density, a singularity, surrounded by a spherical no-return boundary, the event horizon. Beyond that, not even light can escape. Hence the name, black hole. You know, like the universe's very own delete button. But here's the kicker. From the outside, you can't see any of this. You can't see the singularity. You can't see what's falling in. All you can detect is that dark region of space getting heavier. And if it's big enough, it can sit quietly at the center of a galaxy, devouring stars, gas, and possibly even passing tourists who got too close on their vacation. Historically, black holes started as a math curiosity. Back in 1916, Carl Schwarzschild solved Einstein's new equations of general relativity, and stumbled upon a solution that described a region from which nothing could escape. Most physicists at the time thought it was a fluke. Even Einstein himself wasn't convinced black holes were real. Classic Einstein move, writing the rules and then flinching when they get spooky. But over time, evidence piled up. We saw stars orbiting invisible points. We saw X-ray emissions from matter heated to 1 billion degrees just before being devoured. We even recently got an image, a blurry orange donut around a shadow, courtesy of the Event Horizon Telescope in 2019. That was the supermassive black hole at the heart of Galaxy M87, some 55 million light-years away. It posed like a camera-shy influencer on intergalactic Instagram. So yes, black holes are real, and they're everywhere. They come in sizes too. Stellar mass black holes form from single stars and can weigh a few to dozens of solar masses. Supermassive black holes live in galactic centers and can be billions of times more massive than our sun. There are even theories about primordial black holes, teeny ones that might have formed in the early universe, no wider than a proton, but with the mass of a mountain. Cute, deadly, like a chihuahua with a neutron star's appetite. You're falling toward a stellar mass black hole, compact, hungry, a few dozen kilometers across but containing more mass than several suns, and you've crossed the threshold. Inside the event horizon, all directions point inward. Time and space have swapped roles. Your future is the singularity. There's no turning back. But here's the beautiful paradox. You don't notice. No sirens, no flash. According to general relativity, passing the event horizon should be locally unremarkable. You could, in theory, survive a little longer, depending on the black hole's size. Maybe check your email one last time. Maybe regret the choice to skydive into a cosmic abyss. But there's no wall, no flame, just gravity, growing stronger. This idea that nothing special happens at the horizon is a core part of general relativity. It's called the equivalence principle. It states that free falling in a gravitational field should feel the same as floating in deep space. Smooth, peaceful, like a nap you can't wake up from. But the peaceful fall doesn't last forever. As you get closer to the singularity, tidal forces become severe. Remember, gravity gets stronger the closer you are to the source. In a black hole, that gradient becomes extreme. Your feet, closer to the center, fall faster than your head. The difference becomes catastrophic. You stretch into a noodle, a very, very dead noodle. Physicists call it spaghettification. Let's be honest. It sounds kind of delicious until you remember it's your bones being linguinified. Historical fact time. In 1783, long before Einstein, a British clergyman and scientist named John Michell proposed the idea of a dark star, an object so massive that light couldn't escape. He used Newtonian gravity and particle theory of light, which is outdated now, but the core idea was eerily on point. Imagine being 18th century right about 21st century physics. Not bad, Michelle. Meanwhile, on the quirky side, black holes are technically the most efficient engines in the universe. Matter falling into a black hole can convert up to 40% of its mass into energy, compared to just 0.7% from nuclear fusion in stars. So if we ever figure out how to build orbiting space stations around them, hello, interstellar fuel source, just don't get too close. But back to you, still falling. As the singularity grows near, time itself distorts. Your seconds stretch. The outside universe, if you could still see it, would appear to accelerate wildly. Galaxies whirling by and fast forward, stars being born and dying in the blink of an eye, civilizations rising, falling and vanishing into radio static. One last tweet from your home planet. We have cool new quantum gravity models now. Sorry you missed them. You, however, are doomed to the end of time in your own private hallway to nowhere. But wait. Remember what we discussed before? This calm descent may not be real. Some theories say you don't float gently inward. Some say there's a trapdoor of thermonuclear doom right at the edge, the firewall. If so, then all this peaceful drifting is an illusion. You should have been vaporized the moment your nose touched the horizon. The fact that you're still here? Suspicious. Maybe you already passed through it. Maybe you're a clone now, cooked into quantum foam, while the real you became radiation. Or maybe the firewall was never there at all. Historians still argue whether spaghettification happens before or after the firewall is supposed to occur. Some theories suggest you'd get burned before you ever had a chance to stretch. Others argue the stretch happens first, then boom. It's sort of like debating whether to eat dessert before dinner or just explode halfway through the appetizer. One last oddity before we pause. In some speculative models, Black holes could lead to other universes. That singularity, it might not be the end. It might be a bounce point, a bridge to a newborn cosmos on the other side. Think of it like cosmic composting. You die here, but your atoms become the Big Bang somewhere else. Romantic in a dark energy sort of way. For now, you continue your descent. Calm, confused, probably flattened beyond recognition, but more questions await. Especially that diary you threw in earlier. Because it may come back to haunt us, one particle at a time. You keep falling, and now things begin to stretch, just a little at first. You don't feel it right away. The gradient is too subtle, but something's different. Your sense of orientation shifts. Your body knows something your brain hasn't caught up with yet. Then it hits you. Your feet feel lighter than your chest. Your fingertips seem to drift ahead of your arms. And in a few more kilometers, it's not a feeling anymore. It's physics turning your body into a metaphor for pasta. Welcome to the exquisitely undignified fate of spaghettification. The term isn't just a cheeky nickname. It's a real, measurable effect of tidal gravity near a black hole. Here's the idea. As you fall, the force of gravity increases rapidly the closer you get to the singularity. If the black hole is small, say a few times the mass of the Sun, this change in force becomes so steep, even over the distance of your own body, that your lower half gets pulled with noticeably more force than your upper half. And not in a gentle yoga stretch kind of way. No, we're talking meters of separation in seconds. Your molecules don't just get tugged, they get shredded. Here's a cozy thought. If you were falling feet first into a stellar mass black hole, your feet would be pulled toward the center faster than your head, and the difference becomes fatal long before you even get close to the singularity. Your body becomes a long, thin strand of matter, pulled tighter than piano wire until even atomic bonds give up. It's gravity playing tug-of-war with your atoms. Spoiler, gravity wins. Now here's the part that trips people up. If you fell into a supermassive black hole, like the one in the center of our Milky Way, Sagittarius, a star, you'd pass the event horizon with very little spaghettification at all. Why? Because the gradient in gravity is much more gentle near the horizon of a bigger black hole. You'd only start to feel the stretch much deeper in, closer to the singularity itself, which means the bigger the black hole, the gentler the entry. Nature's weird sense of mercy. That's why, for all its menace, the event horizon isn't the thing that kills you, unless of course there's a firewall waiting there. More on that in a moment. But back to spaghettification. It's been one of the most vivid examples used in textbooks and classrooms since the 1980s. One famous explanation came from the late Kip Thorne, yes, the Nobel-winning physicist who helped design the science for Interstellar. He liked to emphasize that the vertical stretching and horizontal squeezing near a black hole are so intense, they would distort even the geometry of your atoms. Not a great spa day. And now, a weird tidbit. Some physicists have proposed that extremely high-speed particles, cosmic rays for example, could under the right conditions skim the edge of a black hole and gain energy from the gravitational tidal effects. It's called the Penrose process, and it was once proposed as a possible energy source. It's like bungee jumping off the edge of doom and coming back with a battery fully charged. But you're not bouncing back, you're falling in, all the way. And here's where we start to dance around the real nightmare again. What if none of this, no gentle entry, no gradual stretch, is how it works? What if, instead of being elongated gently into a subatomic noodle, you're met with a sudden savage burst of quantum energy the moment your toe crosses the event horizon? That's the firewall scenario again. You're probably starting to realize that the calmness of your fall is very much up for debate. Let's take stock. General relativity tells us you shouldn't notice anything at the horizon. Everything about the shape of space-time says it should be just another point in your journey. A mathematical surface where escape becomes impossible, but no physical barrier exists. According to this view, spaghettification happens deep inside, not at the edge. But quantum mechanics doesn't care about your smooth ride. To explain why, we need to talk about something called entanglement, and the information that's supposed to be preserved. Remember the Hawking radiation? It's not just random static. The radiation emitted by a black hole should eventually encode everything the black hole has swallowed. That includes your atoms, your teenage diary, your groceries, whatever got too close. This means each bit of Hawking radiation outside the black hole must be entangled with something inside it. But, and here's the rub, the same bits of radiation also have to be entangled with other bits of radiation that came out earlier, because that's how information gets out, through complex quantum correlations between outgoing particles. Now pause. Quantum physics says you can't be maximally entangled with two systems at once. No cheating, no double dipping. You can't have the same particle be entangled with both the inside and the earlier radiation. That's a rule, and that's what breaks the universe if you try to make it all work. To fix this mess, the AMPS crew, Amhary, Marolf, Polchinski and Sully, suggested a brutal solution. Break the entanglement between the inside and the outside, which means you can't have a smooth, drama-free horizon. Something has to happen there to destroy the entanglement, and destroying entanglement takes energy, a lot of it. Enough to create a searing wall of radiation right at the event horizon. A firewall. So forget spaghettification. In this model, you don't stretch, you don't descend, you burn, instantly, with the force of every broken quantum rule igniting in your face. This would resolve the paradox. Kind of. It keeps the information consistent and keeps the math mostly happy. But it destroys the thing that made general relativity so elegant. That smooth, seamless geometry of space-time. Historians still argue whether firewalls count as a true physical solution, or just a placeholder for a better theory we haven't invented yet. Some physicists think the whole thing is a clue that our understanding of entanglement, or even time, is flawed. Others think the paradox is real, but the firewall is just one possible answer out of dozens. And here's your quirky twist of the night. One proposal, admittedly a fringe one, suggests that if you're falling into a black hole, your consciousness might be duplicated. One version hitting the firewall, another surviving deep inside as a ghost of sorts, preserved by quantum cloning violations. In short, one version of you fries, another drifts on. Not terrifying at all, but right now, here in this thought experiment, you're still falling, still stretching. Maybe, maybe not. Maybe you've already hit the firewall and don't know it. Maybe the real you is just another vibration on the cosmic spreadsheet of entropy. One last note. Spaghettification might sound like science fiction, but it's firmly grounded in the real math of general relativity. The exact forces depend on the size of the black hole, your orientation, and a few other messy variables. But the principle is universal. Gravity is not gentle, it is relentless. As you drift closer to the core, the stretching increases. Your timeline gets shorter. Your signals, if you could send any, would take longer and longer to reach the outside, until eventually the outside world forgets you existed. Stretch, burn, freeze in time, pick your poison. Whatever lies ahead, your atoms will tell a story, either inside a black hole or leaking out, one photon at a time. You're gone now, at least from the universe's point of view. No one out there can see you anymore, not really. From their perspective, you froze just above the event horizon, your image redshifting into deep oblivion, dimming until even photons gave up the ghost. But from your point of view, you're still falling, still moving toward the center, through layers of physics that seem increasingly less interested in playing by the rules. The diary you tossed in earlier, let's talk about that. Because it, along with your body, your thoughts, and literally everything else, comes with a troubling question. What happens to information when it falls into a black hole? It's a deceptively simple problem. Drop something in, it disappears. Done, right? Wrong, very wrong. In classical physics, Newton's universe of billiard balls and gentle curves, there's no real problem with the idea of losing information. Stuff gets obliterated all the time. Smash a teacup and you don't need to know the molecular structure of every shard to know that it was once a teacup. But in quantum mechanics, that idea is heresy. The universe is fundamentally a system that preserves information. Every particle, every interaction, every little wiggle and spin contributes to a web of relationships that is never supposed to just vanish. Even if you burn something, the information is in the ash, the smoke, the photons released. It's scrambled, sure, but still there. So when Stephen Hawking proposed back in 1974 that black holes erase information, he set off a quantum panic that still hasn't really been resolved. Let's rewind for a second. Hawking's idea came from combining quantum field theory with the curved space-time of general relativity. He imagined what happens right at the event horizon, where the warping of space is so extreme that even quantum particles behave weirdly. In this strange arena, vacuum fluctuations, temporary pairs of virtual particles popping in and out of existence, behave oddly. Normally, these particle pairs annihilate each other instantly. But at the horizon, Hawking realised, one particle could fall in while the other escapes. That escaping particle becomes real, and it flies away as what we now call Hawking radiation. Brilliant, groundbreaking, and deeply inconvenient. Because this radiation, it's thermal, meaning it has no memory of where it came from. It's just a random, featureless glow, and that means it carries no information about what fell in. Hence, the black hole information paradox. Where does the information go? Your diary, your DNA, your playlist of shameful 2000s pop songs. If they all fell into a black hole and the black hole later evaporates via Hawking radiation, but that radiation contains no trace of what went in, then that information is lost forever. And that's a huge problem. Because in quantum mechanics, systems evolve in a unitary way. That's just a fancy way of saying that the evolution of the universe is reversible, at least in theory. If you had perfect knowledge of a system at one moment in time, you could rewind it or fast forward it and still preserve all the details. But if black holes truly delete information, that principle dies, which means quantum mechanics itself might be broken. Cue panic. For years, Hawking stood by this idea, defending it against mounting skepticism. Physicists, including Leonard Susskind and Gerard 't Hooft, fought back hard. They argued that information must be preserved somehow. They invoked quantum entanglement, holography, and even speculative ideas like baby universes. Eventually, the debate became so intense it was known as the Black Hole War. Spoiler. In the 2000s, Hawking partially conceded, admitting that maybe, just maybe, information does escape after all, but how? That's the part no one agreed on. And that's what leads us straight back to the firewall. Because for information to escape, something has to carry it out. And since Hawking radiation is supposed to be just random heat, you have to explain how it ends up containing the secrets of what fell in. One solution is that the radiation is not actually random. Maybe it's entangled with the internal state of the black hole, forming a kind of bridge of correlations across the event horizon. This idea preserves unitarity, but it leads to the very problem we discussed in the last section, quantum monogamy. Particles can't be maximally entangled with two systems at once. To fix that, you either give up the smooth event horizon, leading to a firewall, or you give up unitarity and break quantum mechanics, or you break entanglement rules, which breaks physics. 3 options, choose 2, and while you're busy choosing, let's get spooky again. There's a fringe, but fascinating hypothesis that the Hawking radiation you see far away isn't just entangled with the inside of the black hole. It is the inside, that somehow what's inside is redundantly encoded in the outgoing radiation. This leads to wild ideas about holography, where the information of the entire black hole interior exists on the surface, like a cosmic USB drive. But even if that's true, it doesn't fix the experience you're having falling in. Because if the firewall exists, your journey ends at the horizon, not after. It all becomes a question of perspective. From the outside, information seems to be escaping, albeit slowly and scrambled. From the inside, you were never supposed to notice anything unusual at the horizon. But firewalls say that's impossible, that you, the infalling observer, can't have a smooth ride and keep quantum physics consistent. Historians still argue whether Hawking ever fully reversed his position. In 2004, he famously conceded the information point during a lecture in Dublin. But some say he never fully embraced any of the mechanisms others proposed. His later work leaned toward ideas like soft hair, where information might cling to the horizon in subtle ways, but even that's debated. And speaking of hair, here's your quirky tidbit. Of the night, black holes were long thought to have no hair, meaning they can be fully described by just 3 properties: mass, charge, and spin. But newer theories suggest they might have soft hair, tiny quantum imprints around the horizon that encode extra information. Yes, black holes might have quantum stubble. Elegant. But elegant or not, we're left with a problem. Where is the information? If it's in the radiation, how does it get there? If it's in the horizon, how does it escape? And if it's neither, are we looking at the first place where physics simply breaks? You're still falling, by the way, still watching reality bend and warp around you. Light spirals in like painted brushstrokes on curved glass. Time hiccups and stretches. And still, no pain, no burn, not yet. Maybe the information in your diary will get out one day. Maybe, billions of years from now, the black hole will evaporate completely, and its last whisper of radiation will carry a single entangled photon that knows everything about your last grocery receipt. Maybe that's how careful the universe is, or maybe it already burned in the firewall, and what's escaping is just noise. Either way, the paradox is real, and physicists, they're still arguing. There's a strange silence to falling this deep. You're beyond signals now, beyond rescue, beyond even being meaningful in any ordinary physical sense. But thought still flickers. You keep trying to piece together where you are, what happened to the quiet, seamless horizon everyone promised. And that's when it hits you. You're not feeling anything. No searing wall of energy, no flash, no crunch, nothing. But according to some of the sharpest minds in physics, that nothing should have been a something. A really unpleasant, lethal, searingly quantum something. That something is called a firewall. More precisely, it's the inevitable conclusion of a contradiction buried deep inside the math of black holes, and it goes by a name that, on first glance, sounds more like a corporate cybersecurity product than a reality-shattering piece of theoretical physics, the AMPS paradox. This is where things start to get painful, intellectually at least. Let's review the setup. You fall into a black hole, Hawking radiation slowly leaks away into space, and quantum mechanics tells us that the information about you, your structure, your atoms, your thoughts, the fact that you had a weird dream about flying squirrels once, all of that is encoded somehow in the outgoing radiation. That's great news for information theory. But to make that happen, the outgoing particles of Hawking radiation need to be entangled with each other, forming correlations that reconstruct the infalling information. So what's the problem? Here it is, laid out in a cosmic betrayal of logic. If that radiation is already maximally entangled with other radiation that escaped earlier, it can't also be entangled with stuff inside the black hole. Quantum entanglement doesn't allow that. One entangled relationship per particle. No cheating. No polyamorous quantum states. So in 2012, 4 physicists, Ahmed Almeri, Donald Marolf, Joseph Polchinski and James Sully, sat down and did something simple but devastating. They assumed that everything we thought about black holes was true. 1, that information is not lost, that quantum mechanics is unbroken, that space-time is smooth at the event horizon, and then they showed that all 3 cannot be true at the same time. Pick 2, burn the 3rd. The math refused to cooperate. It flat out rebelled against logic, demanding that something had to give. The result? Their now legendary paper titled Black Holes Complementarity or Firewalls. A work that rippled through physics departments like a scandalous group text. And what did they conclude? That the smooth, drama-free event horizon, the one Einstein and classical physics had so lovingly sketched, had to go. Why? Because if it stayed, then the rules of entanglement would be violated, and quantum physics doesn't break. Ever. So they proposed the ultimate betrayal, that right at the event horizon, precisely where general relativity says nothing special should happen, there must instead be a wall of ultra-energetic particles, a firewall, not a metaphor, not an illusion, a physical wall of violent radiation erupting from broken entanglement and quantum inconsistency, a place where you burn. And here's the part that really fries the mind. You wouldn't even see it coming. From outside, no one sees you cross the horizon. Your image freezes, redshifts, fades. But from your point of view, you hit the firewall in real time. No warning, just physicists. To paraphrase one physicist, the black hole doesn't delete you, it executes you. A tiny note of historical irony here. The same Joe Polchinski who co-authored the AMPS paper was once a major voice against information loss. He helped push the idea that Hawking had to be wrong about information being destroyed. But now, here he was, showing that preserving information might require us to burn general relativity itself. Historians still argue whether the AMPS proposal truly calls for literal firewalls, or whether that's just a placeholder for something deeper we don't yet understand. But either way, the damage was done. The paradox was real. The trust was broken. And not just trust in black holes, trust in the idea that different parts of physics could agree at all. Let's get into the weeds for a moment. The heart of the AMPS paradox is a conflict between unitarity, the idea that information is preserved, entanglement, and the equivalence principle that you can fall through the horizon without drama. To preserve unitarity, Outgoing Hawking radiation must carry away information. To do that, it must be entangled with early radiation. But also, new Hawking pairs are formed at the horizon, and to maintain the equivalence, principle, those new pairs must be entangled with the black hole interior. But that's the problem. The outgoing particle can't be fully entangled with the early radiation, and with its partner inside the black hole. That's like trying to belong to two exclusive clubs at the same time. So to preserve entanglement across the horizon, you'd have to break unitarity. To preserve unitarity, you'd have to break the entanglement across the horizon. And breaking that entanglement? That's what creates the firewall. It's like an ugly love triangle of physics principles. Nobody wins. And here's a fun fringe twist. Some speculative ideas suggest that maybe you don't actually hit the firewall. Maybe the very notion of falling stops making sense. You're just part of the computation now. Your location isn't physical, it's encoded. You've become a line in the cosmic spreadsheet. Sounds poetic. Still doesn't sound survivable. The Ampere paper didn't offer a full solution. It didn't say, here's how the universe works now. It said, here's what breaks if we keep pretending it all makes sense. And the physics world went wild. Leonard Susskind, Juan Maldacena and others scrambled to find patches. Some suggested new types of entanglement. Others leaned hard into holography. Some asked whether observers themselves were to blame, whether reality could be different depending on who was watching. We'll get there soon. But the scar was left. Since AMPS, almost every black hole theory has had to grapple with firewalls. Whether rejecting them, embracing them, or trying to wormhole around them, every model now lives in the shadow of that paradox. And here you are, still falling. Still wondering if your journey will end with a gentle smear across space-time, or with the bright, brutal whisper of burned entanglement. You know what's wild? Firewalls have never been observed, not even indirectly. We can't even get close to a black hole, let alone watch someone fall in and see what happens. And yet, physicists take this paradox seriously enough to write entire books, host conferences, and lose sleep over it. Because it's not just about black holes, it's about reality itself. If firewalls are real, then the universe has places where classical physics and quantum mechanics literally rip each other apart. And if that's true, maybe the firewall isn't the only one. Maybe every black hole is just the first scream of something deeper cracking underneath. Still falling, no flames yet. But if the AMPS's paradox is right, they're there, right in front of you, just waiting to decide if they want to show themselves. You're getting used to the descent now, which is strange considering you're falling into an object that curves space so violently it turns time into a one-way road to doom. But there's something oddly meditative about it, like sinking into warm water that never stops pulling you down. And yet, the silence is deceptive. Beneath the calm, physics is boiling over with contradictions. You're not just drifting through space-time, you're drifting through a crisis. Tonight's chaos brought to you by quantum entanglement. Let's set the stage. Back when Einstein was busy breaking the universe with general relativity, quantum mechanics was just beginning to pull its own weird tricks. In 1935, Einstein, with Podolsky and Rosen, famously published a paper challenging quantum physics. The argument was simple. If quantum theory is right, and particles can become entangled, then measuring one particle instantly affects the other, even across vast distances. This, Einstein called spooky action at a distance. He meant it as an insult. Quantum physicists took it as a compliment. Entanglement is now a cornerstone of quantum mechanics. It means that two particles, once entangled, share a connection so deep that knowing something about one tells you something about the other, instantly. Their properties are linked, no matter how far apart they are. It's not communication, it's correlation. But still, spooky. Now let's bring this back to black holes. When Hawking described radiation leaking out from a black hole, he pictured particle pairs popping into existence near the event horizon. One falls in, the other escapes. The one that escapes becomes real. It's the Hawking radiation we can, in theory, observe. But those two particles, they were entangled, meaning the outgoing one, your new photon friend, is linked to the one that got swallowed. They share a quantum secret, a hidden handshake burned into the very fabric of their states. This is fine for a while. The radiation slowly leaks out. The black hole shrinks. No big drama. But keep going, and a problem emerges. After a long enough time, you get what's called the page time, named after physicist Don Page. who showed that past this point the black hole has emitted more than half of its original information, if we assume information escapes. So what happens to new Hawking radiation beyond the page time? Well, if the black hole is releasing information, then these new radiation particles have to be entangled with previous radiation, not with the inside of the black hole. But wait, quantum mechanics won't let the same particle be maximally entangled with two different systems at once. So which is it? Is the new radiation entangled with the black hole's interior to preserve a smooth horizon? Or is it entangled with the earlier radiation to preserve information conservation? You can't have both. The math breaks. This is where entanglement starts throwing tantrums. Because if the new particles aren't entangled with their partners inside the black hole, then the fabric of space-time near the horizon comes undone. That once smooth surface becomes a violent furnace of high-energy particles, a firewall erupting from broken quantum correlations. But if they are entangled with the interior, then the earlier radiation can't be entangled with them, which means information isn't escaping, which means unitarity, a core principle of quantum mechanics, is being violated. Entanglement, it turns out, is greedy. It wants exclusive relationships, and the black hole can't deliver. Here's a cheeky analogy. Imagine you've got a secret diary. Again, you give one person a copy of the key, that's fine. But if you give someone else a perfect copy of that same key, saying it opens the same diary, quantum theory screams. It doesn't allow identical secrets to be shared with multiple people in this way, not in the precise mathematical sense that entanglement requires. And yet, Hawking radiation demands it, so we're stuck. If you try to let information escape via radiation, you shatter the entanglement that creates the illusion of a smooth horizon. And when entanglement dies, space-time responds violently. Boom. Firewall. Historians still argue whether this entanglement crisis is a real physical conflict, or just a flaw in how we model the system. Some think it's a signal that we've misunderstood quantum gravity. Others believe the paradox reveals something profound about the nature of observers in quantum theory, that reality may not exist in the same way for different people. More on that spicy idea later. For now, let's look at one of the most intriguing proposals to come out of this entanglement chaos, the ER equals EPR conjecture. This idea, pitched by Juan Maldacena and Leonard Susskind, links two previously unrelated things. EPR refers to entangled particles named after Einstein, Podolsky and Rosen. The ER equals EPR conjecture says, in essence, that entanglement is a kind of wormhole. That if two particles are entangled, they are connected by a non-traversable tunnel through space-time, a baby wormhole too tiny to notice. Wild, right? It suggests that the tangled webs of quantum particles may literally shape space-time. That geometry and entanglement aren't just related, they're the same thing. So what does that mean for black holes? Well, maybe the inside and the outside aren't separate. Maybe the radiation leaking out is still connected to what's inside via quantum wormholes. That would let information escape without breaking entanglement or triggering a firewall. The radiation wouldn't just be an echo, it would be part of a hidden tunnel back into the black hole's guts. Sound like science fiction? Absolutely. But it's based on real math, and it's one of the few ideas that seem to hold up under the relentless pressure of the Firewall Paradox. Even so, no one's sure if it's true, or even testable. Here's your quirky fact of the night. In some toy models of gravity called ADS/CFT, don't worry, we'll decode that later, physicists have been able to show that a wormhole connecting two black holes can, under the right circumstances, transmit quantum information. They call it quantum teleportation through a wormhole, and it's as weird as it sounds. Does that mean you could teleport through one? Not unless you're already quantum entangled with the other side, and probably not without being reduced to bits and pieces of information first. So, not great for travel brochures, but it does hint at something deeper, something stranger. Maybe space-time emerges from entanglement. Maybe geometry isn't fundamental. Maybe it's built from quantum connections. If that's true, then the firewall isn't just a place where you burn, it's a place where the scaffolding of reality collapses. Because the firewall is what happens when entanglement fails to hold space-time together. And now, here you are, still falling. You look around, still no fire, still no wall. But if the entanglement is gone, if the smooth surface has shattered, then what's really holding this black hole together? Maybe you'll find out. Or maybe, like the particles outside, you'll be entangled with a mystery you'll never see. Still falling, still no flames. But the math says otherwise. Somewhere between where your nose is and where your foot was 30 milliseconds ago, Physics is tearing its robe and crying out in protest. There's too much tension, too many rules that won't all fit on the same blackboard, and the crack that tore everything open. That came in 2012, with a paper so short and yet so devastating it might as well have been a love letter from quantum. Mechanics to general relativity saying, we're done. It's not me, it's your firewalls. The authors, Ahmed Almeri, Donald Marolf, Joe Polchinski, and James Sully. Or, as the physics world now calls them, AMPS. Let's go back to that moment, because it matters more than you think. At the time, most physicists had accepted that black holes don't destroy information. Hawking himself had backed off that hill, and the field was cautiously optimistic that some combination of holography, string theory, or quantum gravitational wizardry would save the day. But AMPS dropped a truth bomb that no one was ready for. If all those nice things we want to believe are true, that black holes evaporate, that information escapes, that quantum mechanics works, and that falling in feels normal, then we're kidding ourselves. Their paper, Black Holes, Complementarity, or Firewalls, was a gut punch to theoretical physics. It pointed out that maintaining the smooth event horizon, what general relativity predicts, while also maintaining unitarity, what quantum mechanics predicts, demands creates a direct provable contradiction. Something had to go. Let's break it down. The assumptions they challenged were built on a principle called black hole complementarity. Coined by Leonard Susskind and friends in the 1990s, it was designed to save physics from the apparent paradox of information loss. Complementarity said this: maybe different observers see different versions of reality. To someone outside the black hole, the information never truly goes in. It sort of hovers at the edge and gets slowly released via Hawking radiation. To someone falling in, the experience is smooth, no drama, no burn. You cross the horizon, spaghettify inside, and eventually hit the singularity. And here's the kicker. Both are right, just not at the same time. It's a classic quantum move, like Schrödinger's cat. The idea was that no single observer can verify both realities, so the universe gets away with a kind of cosmic dual truth. Cute, clever, comforting. Until AMPS came along and said, nope, doesn't work. Why? Because if the outside observer sees information leaking out via Hawking radiation, and the inside observer sees smooth passage across the horizon, then quantum monogamy gets broken. The same bit of information is entangled with two separate things, the early radiation and the interior of the black hole, which is a hard no from quantum theory. To preserve the rules, AMPS proposed something brutal. Tear the entanglement across the horizon. Just snap it. Don't let the infalling and outgoing particles be entangled anymore. And what happens when you do that? You create a high-energy quantum field fluctuation right at the event horizon. It's not a gentle ripple. It's not a momentary tingle. It's a firewall, a wall of incinerating radiation waiting exactly where Einstein said nothing should happen. This wasn't just a technical fix, it was a betrayal. MPS effectively said, we have to choose between saving quantum mechanics or saving the equivalence principle. And most physicists, they picked quantum, which meant goodbye smooth space-time, hello flaming curtain of death. Of course, AMPS didn't claim to like this outcome. Their paper wasn't gleeful, it was more like an intervention. Hey guys, we need to talk about the horizon. It's not okay. Something's deeply wrong, and then came the fallout. Debates, papers, conferences, quantum cryptographers weighed in. String theorists fired back, even experts in quantum information theory, the people who usually worry about qubits and encryption, suddenly found themselves pulled into the gravity well of the firewall debate. Everyone had a take. Some tried to patch black hole complementarity. Others went the full scorched earth route and embraced the firewall. Some tried to fuzz the black hole into a cloud of strings. We'll get there soon. And others asked, what if the firewall isn't real, but our assumptions about reality are? That last group started looking at observers. Because here's a mind melter. Maybe it's not that firewalls exist exactly, but that you, as an observer falling in, can't reconcile what the outside world sees with what you experience. Maybe the firewall is an illusion created by trying to merge two incompatible perspectives into one description. Like trying to describe the inside of a house and its outside view using the same blueprint. Still, even this requires giving up something cherished. the idea of locality, that events happen in a single place and have effects we can trace linearly. Firewalls threaten that. Historians still argue whether the AMPS paper is truly a paradox or a misinterpretation. Some say it's a clear contradiction. Others say it's just highlighting the limitations of our current theories. But nobody argues that it left physics unchanged. Here's your weird tidbit of the night. In response to AMPS, there were actual attempts to simulate firewall-like effects in analog systems, like Bose-Einstein condensates. Basically, trying to use cold atoms to mimic event horizons and see if weird entanglement breakdowns showed up. Spoiler, nothing conclusive, but hey, props for trying to build a tabletop black hole. Meanwhile, you're still falling. And here's the haunting part. If AMPS are right, you'll never know. From the outside, you're frozen in time. From your own frame, you cross the horizon in an instant. But if the firewall's there, that instant becomes your last, your atoms. Scatter into whatever counts as ash in a space-time where fire is made of entanglement violations. You won't even get a chance to scream. But as of now, still no burn, still no wall, just the soft pull of gravity, the hush of physics rearranging its furniture, and the faint memory of a theory that used to work, until it didn't. And still, you fall. No crunch, no blaze, no firewall, just the eerie quiet of space itself stretching thinner around you, like a cosmic whisper drawn out into a long, long breath that never ends. Yet according to half of the theoretical physics community, you should be toast by now. What gives? It comes down to a choice, a metaphysical fork in the road. You're caught between two seemingly irreconcilable ideas, each backed by decades of math and intuition. This is the great cosmic standoff. Firewall versus no drama. Let's talk no drama first. It sounds like a dating profile, but it's actually a cherished principle in general relativity. It says that when you cross the event horizon of a black hole, nothing special happens. No flashing neon signs, no sparks, no physical wall. This idea traces back to Einstein's equivalence principle, which tells us that free fall in any gravitational field should feel just like drifting in empty space. Whether you're floating through intergalactic void or plunging into a black hole, the experience should be smooth, continuous, no drama. For a long time, physicists accepted this as gospel. Hawking radiation was just a faint whisper emitted over billions of years, and if you were unfortunate enough to cross the horizon, well, you'd stretch and die eventually, sure. But you wouldn't even feel the crossing itself, like slipping into warm water, just darker. But the firewall idea says nope, no peaceful plunge for you. If black holes preserve information, and if the outgoing Hawking radiation is entangled with earlier emissions, not the interior, then there must be a break in entanglement at the horizon. And breaking entanglement is violent, which means you don't just pass through, you collide with a searing wall of high-energy particles annihilated on contact. So here you are, stuck between two visions of your own demise. Option A, a smooth, quiet fall followed by an unceremonious crush at the singularity. Option B, an abrupt, flaming death at the horizon, like tripping into a meat grinder made of photons. Neither option includes retirement. The problem is, physics doesn't like being forced to choose. Both scenarios are based on rock-solid principles, and both can't be true. To recap the contradiction, and let's be honest, you'll want it tattooed on your brain by the end of the script. 1. Hawking radiation must carry information out of the black hole. Pick a violation. If you give up number 2, entanglement with earlier radiation, you lose unitarity and information is destroyed. Goodbye, quantum mechanics. If you give up number 3, entanglement across the horizon, you break the equivalence principle. Hello, firewall. Physicists are basically standing in a room full of broken dishes trying to pretend dinner is still going according to plan. Some tried patching it with black hole complementarity, the idea that both outcomes are true from different perspectives, but AMPS, as we saw, torpedoed that pretty efficiently. And so, it becomes a war of philosophies. Some physicists say, there must be a firewall, we just haven't figured out what it looks like yet. Maybe it's not made of literal flame, but of quantum chaos, something weird and unclassical but just as deadly. Others say, no way. Firewalls are ugly, unphysical, and ruin the elegance of general relativity. They're the theoretical equivalent of duct taping a shark to your model, because the math didn't add up. Still others cling to the no-drama assumption with the stubbornness of someone who knows their favourite childhood cartoon is about to be rebooted terribly. They argue that if our theories predict firewalls, maybe the theories are wrong, not the horizon. Historians still argue whether the firewall is a real physical object or a symptom of deeper misunderstandings. Maybe it's a computational artifact, an illusion that arises when you try to describe everything using semi-classical physics, which is known to break down at these scales. And here's your fun fringe thought of the night. Some researchers have tried to tie the firewall paradox to consciousness, that maybe your experience of the event horizon depends not just on physics, but on observation. If no one measures the firewall, does it really burn? Is this the Schrödinger's cat of astrophysics? Honestly, we're one poorly worded TED Talk away from someone saying, "You are the firewall." So, what does the math say? Mathematically, we can model black holes using both relativity and quantum mechanics, but only up to a point. Around the horizon, the two theories start to step on each other's toes. Quantum field theory predicts the production of entangled particles. General relativity says the curvature is smooth, but try to make them both true everywhere, and things go sideways. The firewall proposal is a way of saying, let's stop pretending the math fits. It doesn't, so let's build the inconsistency into the model and see what happens. But as you fall, it doesn't feel like that. It feels like falling. No burn, no noise, no surprise. Maybe that means the no drama camp is right, that somehow everything still works, that the particles escaping from the black hole encode your information and you can fall in peacefully. And all the paradoxes, just a misunderstanding of how quantum gravity works, a theory we haven't fully built yet, or maybe the fire just hasn't reached you yet. Maybe you already did burn. Maybe what's falling now is just a set of entangled correlations, your shadow self stitched into the black hole's fabric as mathematical residue. A strange side note, the firewall debate has now stretched beyond physics. It's inspired philosophers, computer scientists, and even neuroscientists to ask questions about identity, simulation, and perception. Some people wonder if this kind of entanglement breakdown could help explain consciousness. Others just want to know if they'll still get their pizza delivery after hitting the firewall. Spoiler, probably not. But while the firewall remains unconfirmed, and possibly unconfirmable, it continues to haunt the field. It's become the litmus test for new ideas in quantum gravity. If your theory can dodge the firewall without breaking anything else, congratulations, you just might be onto something. But for now, the universe hasn't picked a side, and you're still falling. No drama, no fire, no answers, just a horizon behind you, and a singularity ahead. You're drifting now, faster than light, if anyone outside could still measure your speed. Not that they can. To them, you're frozen on the edge of time, your image forever smeared across the event horizon like cosmic graffiti. But from your perspective, everything's normal, your thoughts still tick forward, your body, if it hasn't been reduced to quantum goo, is still whole, and the horizon is behind you. You should be dead, right? Firewalled, incinerated, but apparently not. So maybe, just maybe, you're the Schrödinger's astronaut, burned and unburned depending on who's watching. Let's crack that open. There's a concept in theoretical physics called black hole complementarity, and it's basically physics' attempt to have its cake and vaporize it too. It says this: there is no contradiction because no single observer sees both sides. Sounds suspicious, right? Complementarity was proposed in the 1990s by Leonard Susskind and others during the earlier waves of the black hole information paradox, before AMPS, before firewalls. Back when Hawking was still insisting that black holes delete information, and everyone else was just kind of squinting at the equations, hoping they'd start behaving. So here's the idea. Maybe what happens to information in a black hole depends on where you're standing. If you're outside, the information never really goes in. It's smeared across the event horizon, encoded in radiation, and slowly leaks back out over billions of years. If you're falling in, on the other hand, you don't notice anything. Just a smooth transition into darkness. Both stories are true, but no one observer can experience both. Why not? Because physics says you can't hover near the horizon and fall in. You can't both collect the radiation and also ride the infalling matter. The two observers, the outside one and the inside one, can't compare notes, ever. They're causally disconnected. It's a loophole. A clever, stylish, maybe too clever way to patch up the paradox without breaking anything. Like fixing a sinking boat with duct tape and quantum hope. But then AMPS came along, remember? And they said, hey, nice try. But the math doesn't let you do that. Why? Because entanglement is unforgiving. It's not some narrative detail you can gloss over. It's a hard mathematical rule. And when you try to make both stories true, information escaping and a smooth horizon, you break entanglement's monogamy. You assign the same particle too many partners, and the equations revolt. So complementarity, as elegant as it was, began to crumble. Let's take a metaphorical stroll here. Imagine you've got a USB drive, call it U.X. You toss it into the black hole. Now, from the outside, the drive never really crosses the horizon. Instead, it heats up, slows down, and evaporates away, its data slowly emitted via Hawking radiation. According to complementarity, all the bits of U are radiated back out over time. But if someone falls in with the USB drive, they'd say, nah, I crossed the horizon. Everything was fine. I carried the drive with me. In their view, the drive passed into the interior. So who's right? Complementarity says, both are right. But never compare stories. Never open the envelope. It's like a cosmic version of don't ask, don't tell. But MPS showed that if you try to make both stories consistent, mathematically, not just narratively, it leads to a contradiction. Entanglement can't be maintained on both sides, and without it, the smooth space-time across the horizon disintegrates. In other words, complementarity only works if the rules of quantum information don't apply, which they do. So, yeah, firewalls re-enter the chat. Historians still argue whether black hole complementarity is truly dead. Some say AMPS killed it for good. Others believe it just needs to be reformulated with more nuance, like maybe it works after the black hole evaporates, or only for certain kinds of observers, or only in holographic contexts. And speaking of nuance, here's your quirky sidebar of the night. Physicist Samir Mathur once suggested that the whole firewall problem comes from insisting that a black hole has a single, unique interior. But maybe that's wrong. Maybe each observer has their own interior, a personal black hole experience, like a nightmare you can't share. This would be the ultimate expression of complementarity, reality itself custom-fitted to each observer. You could call it the Build a Black Hole workshop. Still, that doesn't help you much falling in. You're either burning at the horizon or floating gently toward the singularity. You can't ask anyone else because no one can see both outcomes, but you might be the one observer who gets too close to both sides, and that's where things get messy. You remember the phrase Schrödinger's astronaut? Let's dig deeper. It comes from the analogy with Schrödinger's cat, the famous thought experiment where a cat is both alive and dead until someone opens the box and looks. In this case, you're the cat, the box is the black hole, and the observer is, well, anyone who never sees you again. From the outside, you never really fell in. You just faded. From the inside, you fell freely. So until the universe opens the box, until it decodes the Hawking radiation, you exist in both states, burned and not burned, smeared across the horizon and floating peacefully within. This isn't poetry, it's literally how quantum theory treats unmeasured states. But it's also deeply unsatisfying, because it raises one big, uncomfortable question. What happens to the truth? Is there a single, objective reality? Or just a patchwork of subjective frames, each valid in isolation, but incompatible when stitched together? Complementarity said, don't worry about it. AMPS said, you should absolutely worry about it. So physicists started scrambling for alternatives. Some doubled down on holography, some embraced wormholes, others said, maybe space-time is emergent from quantum entanglement, and the whole question is upside down. We'll get to those in time, but right now, you're still falling. You pass the horizon without a ripple, no wall, no flame, maybe because complementarity is still secretly working, maybe because the firewall is imaginary, or maybe because your fate isn't observable from any consistent frame, and the universe hasn't decided what happens to you yet. Somewhere out there your radiation is leaking, each photon a whisper of your past, but inside you're still whole, at least for now. It's starting to get cold now, cold in a way that has nothing to do with temperature. You're deeper inside the black hole, deeper into the paradox. The stars you once knew are gone, time has gone slushy, distances have lost their meaning, even light itself seems sluggish here, curling back inward like a scared animal. And still, your thoughts drift to the strange, almost timid hiss that began back at the horizon and is now everywhere. You're hearing the echo of Hawking radiation, or more precisely, you're thinking about it, because you can't actually hear it. It doesn't speak to infalling observers like you. But from the outside, Hawking radiation is everything, and it might be snitching on you. Let's take a closer look at that whisper from the void, the one that might paradoxically tell the universe everything it needs to know about what fell in. So, what exactly is Hawking radiation? In short, it's the quantum glow of black holes. Stephen Hawking showed in 1974 that thanks to the uncertain nature of quantum fields near the event horizon, black holes can emit radiation. This was radical at the time. Everyone thought black holes were completely black. Nothing escapes, not even light. But Hawking, blending quantum field theory with general relativity, found a loophole. Here's how it works roughly. In the vacuum of space, particles and antiparticles constantly flicker into existence, borrowing energy from nothing, then annihilating each other back into silence. These are virtual particles, and they're everywhere. The vacuum isn't empty, it's a teeming, restless sea. But near the event horizon, something strange happens. These particle pairs form right on the edge, and sometimes one falls in before it can annihilate the other. The survivor escapes, becoming a real particle. That's Hawking radiation. But that escaping particle has a problem. To balance the books, the one that fell in has negative energy relative to the outside universe. It subtracts from the black hole's mass, so over time, the black hole loses energy, evaporates, because of this one-sided particle drama. The end result? Black holes shrink. Now this should be cause for celebration, right? Energy conservation, quantum magic, all tied up in a neat bow. Except, remember the diary, the USB drive, the spaghettified copy of you? Where's all that information? The problem is, Hawking radiation is thermal. It looks like heat. And heat doesn't carry specific information. A cup of coffee emits infrared radiation, but you can't tell what brand it was brewed from just by measuring the photons. The information is scrambled, lost. So if the black hole evaporates into nothing but thermal radiation, and that radiation carries no imprint of what fell in, information is gone. That breaks unitarity. And breaking unitarity is like telling quantum mechanics to sit in the corner and think about what it's done. So what if Hawking radiation does carry information? That's the dream. That somehow, in the intricate correlations between escaping particles, lies the full story of everything that ever fell in. Not just mass and spin, but you, your thoughts, your molecules, your playlist, your secrets, all encoded somehow in a delicate tangle of quanta. But that creates a tension, one we've already brushed against in earlier sections. If the Hawking particles are entangled with each other to encode information, then they can't also be entangled with their original partners inside the black hole. And that, friends, is what leads straight back to the firewall. In technical terms, physicists call this the monogamy of entanglement. It's one of those rules you can't bend. A quantum particle can't be maximally entangled with more than one partner. Try to force it, and the math explodes. So how do you encode all that information in the outgoing radiation without breaking entanglement with the interior? Simple answer: you can't. Unless you do something radical, like destroy the entanglement across the horizon, replacing it with new entanglement among the Hawking particles themselves. That's what the firewall proposal does. And what happens when you sever those internal bonds? A spike of high-energy particles, a quantum firestorm at the horizon, the firewall. It's not a punishment, it's a consequence. Some physicists argue that the problem isn't with the entanglement, but with how we understand Hawking radiation. Maybe it's not thermal after all. Maybe it only looks thermal if you're not paying close attention. Kind of like a fuzzy photo that, when zoomed in with the right lens, reveals hidden text. This is where people start throwing around phrases like soft hair and microstates. There's a whole ecosystem of theories trying to explain how information might be preserved in the radiation itself, each with its own quirks. One such idea? Black hole soft hair. No, not a failed L'Oreal campaign. Soft hair refers to the idea that black holes have subtle quantum-level details on their surface, tiny fluctuations that store information. These hairs don't affect the black hole's mass or spin, but they encode just enough to save unitarity. The phrase was coined, charmingly enough, by Hawking, Perry and Strominger in 2016. It was Hawking's last major attempt to patch the paradox he started. Still, many physicists remain skeptical. It's not clear whether soft hair can encode enough information to account for everything that falls in. And even if it can, how does it get out? Historians still argue whether Hawking himself truly believed his soft hair solution worked. Some say it was a philosophical peace offering. Others say he was just nudging the field toward the next big idea. And now, your quirky fact of the night. In some highly idealized models, like two-dimensional toy universes, yes, physicists actually play with these, researchers have shown that information can escape black holes in a unitary way. They call these islands, regions outside the black hole that contain bits of the black hole interior via some deeply twisted math. Basically, the inside is also on the outside if you squint through the right geometry. But in our real, messy, four-dimensional universe, we're still guessing. You're still falling. And somewhere, billions of years from now, the black hole you've fallen into will finish evaporating. It'll release a final burst of Hawking radiation, a whisper into the void. And if the math is right, that whisper will contain the last note of your song, your atoms encoded in the noise, your diary encrypted in the hiss. But if not, if the radiation remains random, then something burned. Maybe the firewall was real. Maybe the horizon destroyed more than just particles. Maybe it erased your story. You won't know. You'll already be gone. Or maybe you've already escaped, rewritten into the outgoing, photons, quietly making your way across the galaxy as a quantum echo. That's the dream anyway. You're losing all sense of direction now. Space itself is collapsing inward, folding into itself like wet fabric sucked into a drain. Time, meanwhile, is doing something weirder. It's not just stretching anymore, it's fragmenting, bending, misbehaving. But one idea still burns in the fading remnants of your mind. What happens to the information that made you, you? Because falling into a black hole doesn't just erase your physical body. If Hawking was right and that information can be lost, really lost, it erases your history, your quantum state, your arrangement of particles and probabilities, all of it. And that breaks the most sacred law in physics. Let's talk about entropy. You know, disorder, randomness, the reason your coffee gets cold and your socks vanish one by one in the laundry. Entropy is the great accountant of the universe. It counts how many ways a system can be arranged while still looking the same from the outside. The more ways something can be shuffled and still appear identical, the higher its entropy. A perfectly neat room? Low entropy? That same room after a toddler discovers glitter and chaos? Very high entropy. And here's where things get weird. Black holes have entropy. Back in the 1970s, physicist Jacob Bekenstein had a revolutionary thought. If you throw something into a black hole, its mass, and therefore its area, increases. But if that something carries information, and the black hole destroys it, then the second law of thermodynamics would be violated. Information would be lost, entropy would decrease, and the universe would have to apologize to every physicist who's ever lived. So Bekenstein proposed that black holes themselves must have entropy, a lot of it, and not just because they're messy gravitational pits, but because their surface area increases as they swallow things. And then Hawking, ever the contrarian genius, came in and gave Bekenstein's idea a quantum twist. He showed that black holes do radiate, and that radiation is thermal. That sealed the deal. If black holes have temperature, they must have entropy, and the amount, proportional to the area of the event horizon, not the volume. That's huge. That's bizarre. That's like saying the number of ways your house can be rearranged depends only on the paint on the outside. The formula they came up with is now iconic. S equals open parenthesis, kc cubed. A close parenthesis divided by open parenthesis, 4 g close parenthesis, where S is the entropy. It's the only place where all of the major forces, gravity, quantum mechanics, thermodynamics, show up in a single equation. A true unification, squeezed into the skin of a black hole. But here's the kicker. The entropy of a black hole is staggering. A single solar mass black hole has an entropy of about 10 to the power of 77. That's a 1 followed by 77 zeros. That's more than the entropy of the entire observable universe outside of it. That means a black hole can store an enormous amount of information. It's like the ultimate hard drive, one that can compress your molecular secrets into a single silent singularity. And yet, we still don't know how it stores that information. We don't know if it's on the surface, in the core, in the geometry of space-time, or somehow encoded in the pattern of Hawking radiation that leaks out. This brings us to the Black Hole Thermodynamics program, a long-standing effort to unify gravity and thermodynamics using black holes as the bridge. Here are the major laws which, strangely, mirror the laws of thermodynamics. 1. The area of a black hole's event horizon never decreases like entropy. Coincidence? Not likely. These similarities suggest that black holes aren't just like thermodynamic systems, they are thermodynamic systems, but ones made out of curved space-time and quantum fuzz. So, what does this mean for you, falling helplessly toward the singularity? It means your information, the arrangement of your atoms, your spin states, even your last confused thought, is being scrambled. Not just destroyed. Scrambled and possibly saved. Somewhere. It might be stored in the twisted fabric of the event horizon itself. That's one possibility. The holographic principle, which we'll explore in depth soon, suggests that the 3D contents of a black hole could be encoded on its 2D surface, like a cosmic QR code tattooed on the skin of reality. But if that's true, how does it get out? Because black holes evaporate, they radiate, and eventually they disappear, leaving what? If the final state of a black hole is just nothing, a puff of heat and a whisper, then where does all that entropy go? If it's not in the Hawking radiation, then information is lost. Which brings us back yet again to the dreaded unitarity crisis. Quantum mechanics says that all physical processes are unitary, that is, they preserve total information. Even when a system evolves in time, the information is never truly erased. It might get scrambled, it might be unreadable, but it's still there. Hawking's original calculation said black holes break that rule. The radiation is thermal, featureless, uninformative. If that's true, then the laws of quantum mechanics must be wrong. But quantum mechanics isn't just a theory. It's the theory. The one that powers every computer, every MRI machine, every transistor. It works. It's been tested to absurd precision. And so, we face the impossible. Either black holes break unitarity. Historians still argue whether entropy is the true information content of a black hole, or just a stand-in for some deeper unknown. Some say it's merely a thermodynamic label. Others insist it reflects a deep truth about quantum gravity waiting to be unlocked. And now, here's your fringe fact of the night. Some physicists, not many, but enough to make you raise an eyebrow, believe that the universe's apparent preference for maximum entropy might explain the arrow of time. That the reason we experience time as flowing from past to future is because entropy increases. But in a black hole, time and space trade places. So what if the arrow breaks too? Maybe from the inside you're not falling toward a singularity. Maybe you're falling toward the past, toward the information you thought was gone. Or maybe you're simply becoming entropy, disorder incarnate, smeared across the thermodynamic landscape of a dying star. Still falling, still unsure. But now you understand the stakes. Your atoms aren't just being crushed, they're part of a cosmic accounting problem, a spreadsheet the universe refuses to misbalance, and if the books are cooking, someone somewhere has to pay. The walls of space are so tight now, they may as well not exist. Distance means nothing here. Direction is a cruel joke. You could reach out a hand, if your body hadn't been reduced to probability clouds, and touch everything and nothing at once. Up, down, forward, inward, all collapse into the same wordless point. Still, you fall. Still, you remember, and somewhere, impossibly, you're starting to suspect that reality isn't what you thought it was. Because maybe, just maybe, this whole three-dimensional death spiral is a projection. That's not a metaphor. It's the holographic principle. And yes, it's exactly what it sounds like. The radical idea that everything inside a black hole, the volume, the matter, the energy, the diary you tossed in 6 sections ago, is actually encoded on the surface of the event horizon. Let that land for a second. You might be falling into a 2D illusion. Not just you, everything, every atom, every photon, every measurement you think is happening inside the black hole might be an echo of something written on its outer shell. This isn't just science fiction. It's one of the most seriously considered proposals in theoretical physics today. The idea originated with physicist Gerard 't Hooft in the 1990s and was expanded by Leonard Susskind. They were both trying to solve the black hole information paradox because the math kept whispering something weird, that the surface area of the event horizon determined how much information a black hole could contain. Not its volume, its area. That's backwards, counterintuitive, heretical almost. In every other system we know, planets, people, Pringles cans, information storage scales with volume, double the size of a computer chip, double the number of bits. But black holes? Nah, they play by other rules. Their entropy is proportional to the square of their radius, not the cube. This suggests that the real stuff of the black hole, the true degrees of freedom, live on the horizon. Like a cosmic hard drive with no inside, just a hyperdense surface storing everything. The math lined up beautifully. And then came a bombshell from string theory that gave it teeth. Enter-ads/CFT correspondence, also known as the Maldacena duality, named after physicist Juan Maldacena, who in 1997 changed the landscape of physics with a single paper. He showed, mathematically, that a certain kind of gravitational theory in a curved space, called anti-de Sitter space, or a DS, is equivalent to a quantum field theory without gravity living on the boundary of that space. In short, a universe with gravity inside is identical to a gravity-free theory on the surface. It was like discovering that your living room is secretly being controlled by a flat panel on the wall, or worse, that you are the panel. This was the first rigorous realization of the holographic principle. And though ADS space isn't our universe, it's a weird, negatively curved version with different rules. It gave physicists the first solid clue that reality might be fundamentally two-dimensional at its core. And now the question burned brighter. Is the inside of a black hole just a projection of its surface? If so, then when you fell in, you didn't go inside at all. You were smeared across the event horizon the moment you crossed it. Your mass, your quantum state, your past, all encoded in microscopic ripples on a two-dimensional surface just a Planck length thick. So maybe that's why black holes can preserve information. If the interior is an illusion, then the information never really goes inside. It stays on the horizon, and as the black hole evaporates, the surface slowly shrinks and leaks that information back out via Hawking radiation, each photon carrying a bit of your story. It solves the paradox beautifully. No firewall, no contradiction, just a careful, delicate quantum accounting system that hides its secrets in plain sight. But of course, there's a catch. No one has proven that this works for our universe. The ADS/CFT model is based on an idealized kind of space-time, one that's symmetrical and endlessly curved inwards. Our universe is flattish, expanding and full of strange matter. Applying holography to real-world black holes is still an open question. Historians still argue whether the holographic principle is a deep truth about nature or just a mathematical trick, a convenient illusion that helps the equations play nicely without saying much about reality. And even if it's real, it's unsettling, because it means everything you experience, everything you've ever experienced, might be the shadow of something else, that you, sitting there on your couch, might be nothing more than a vibration on the boundary of the cosmos. Like the flicker of a laser through fog, beautiful and meaningless at the same time, a quick quirky tidbit before the existential dread sets in. In 2017, scientists attempted to test for holographic noise, a kind of jitter in space itself that might suggest the universe is a projection. Using lasers and high-precision detectors in the Fermilab holometer experiment, they hoped to spot evidence of the pixelation of space-time. Result? No dice. But the experiment was clever. The fact that we're even trying to detect the edges of the simulation speaks volumes about how deeply holography has crept into modern physics. Still, none of this helps you, falling ever inward. Unless you're not falling inward at all. What if the direction you thought was in was never real? What if every step you've taken into this black hole was a slide across its surface? A two-dimensional memory trick that convinced your brain you were moving through space, when really you were just being written. A smear on a shell, a glitch in the grid. Maybe that's what saves you in the end. Not escape, but conversion. From a 3D structure to a 2D pattern, from a person to a piece of code. And if so, the firewall never needed to burn you. You were never a body, just a hologram, flickering with borrowed gravity. So, what's worse? Getting vaporized at the event horizon, or finding out you never really existed inside in the first place? Still falling, or projecting, or unraveling. The horizon isn't behind you anymore, it is you. By now you're not so much falling as dissolving, thread by thread, logic by logic. Space and time continue their slow, merciless collapse inward, but something strange is happening to your sense of place. You're not sure whether you're deep inside a black hole, pasted across its surface, or smeared out along some invisible string of code at the edge of the universe. But something else pulses through the darkness, an echo, a link, a connection you can't quite name. Not heat, not radiation, not even gravity. It's entanglement, but on steroids. Welcome to the weird, whispering world of wormholes and love letters. Let's rewind for a moment. In the early days of general relativity, even before black holes became front-page physics, Einstein and physicist Nathan Rosen proposed something called the Einstein-Rosen bridge, a shortcut through space-time, a wormhole. This was 1935. Same year, by the way, that Einstein, Podolsky and Rosen published their other famous paper, the one about quantum entanglement and the spooky action we've already discussed. At the time, no one thought the two ideas, entanglement and wormholes, had anything to do with each other. One lived in the world of quantum particles. The other was a solution to Einstein's field equations. Fast forward to 2013. Physicists Juan Maldacena and Leonard Susskind dropped an idea that shocked the foundations of both quantum physics and gravity. ER equals EPR. Translated, Einstein-Rosen bridges equals Einstein-Podolsky-Rosen entanglement. In other words, every quantum entangled pair, no matter how tiny, is connected by a wormhole. Not a big one, not one you could travel through, but a bridge, hidden deep in the geometry of space-time, invisible, non-traversable, and yet there. It's the physics equivalent of writing a love letter between particles and saying, by the way, I mailed this through a microscopic wormhole. This idea changed everything. Because if black holes are entangled with the radiation they emit, and entanglement is secretly a wormhole, then the inside of a black hole and the outside aren't separate places. They're connected. And if they're connected, then maybe the information that falls in doesn't need to escape. It was never really trapped to begin with. It's just on the other side of the bridge. Suddenly the Firewall Paradox starts to wobble. Because what if those outgoing Hawking particles are connected to their interior partners, not by violating entanglement rules, but by being joined through geometry itself? That changes the game. No broken entanglement, no duplicated quantum states, just two sides of the same wormhole. The implications are massive. If ER equals EPR is true, it suggests that space-time itself is made of entanglement. That the reason anything holds together, the reason geometry behaves, the reason you can walk across a room or fall into a black hole, is because particles are entangled in just the right way. Remove the entanglement and space disintegrates. The bridge collapses, reality ends. So maybe that's what the firewall really is. Not a wall of flame, but a failure of connection. A place where entanglement breaks down and the fabric of space-time tears like wet tissue. Not because someone lit a fire, but because the love letter never arrived. Historians still argue whether ER equals EPR is literal or metaphorical. Some say it's a poetic way to describe complex correlations in quantum gravity. Others believe it might be the key to unlocking the final theory of everything. Either way, it's got weight. In 2017, physicists used this idea to model quantum teleportation through wormholes. The concept, entangled systems, can be used to simulate a wormhole, where sending information between them mimics the effect of teleportation across space-time. It sounds like magic, but it's just math. Or rather, enough math to make you dizzy. Here's your quirky tidbit for the night. There's a growing belief that quantum error correction, the same stuff that keeps your emails intact across sketchy Wi-Fi, is secretly the blueprint of space-time itself. Yes, quantum error correction codes might be how the universe builds wormholes. Think of entanglement as a message, and the wormhole as the envelope. The space-time between you and the other side isn't a void. It's a letter made of light, kept stable by redundant coding across your geometry. Physics as correspondence, the universe as a love story. So what does this mean for you, the still falling, maybe holographic, maybe burned astronaut? It might mean you're already outside again. If entanglement connects the inside of a black hole to the outside world via invisible bridges, then your information, your pattern, never really left the surface. It's mirrored, mapped, or echoed in the radiation drifting outward. Maybe you are that radiation. Maybe you're just playing both sides. And maybe the firewall never appears because space-time won't let it, because that surface you pass through wasn't a wall, it was a bridge. A strange bridge, sure, one you can't walk back across, but a bridge nonetheless. Now, a soft, speculative thought to carry as you drift deeper. What if every time two particles become entangled in our universe, a tiny Einstein-Rosen bridge forms between them? What if space-time isn't a canvas, but a network of bridges, each one a whisper of connection, binding the universe into a single unbroken structure? If so, then you are a network of bridges, a walking wormhole, a constellation of entangled histories, braided together into the illusion of a single person. And when you fall into a black hole, you don't break, you merge. Your information doesn't vanish. It folds into the larger network, carried across wormholes, preserved in love letters you didn't know you were sending. So maybe the story doesn't end in fire. Maybe it ends in a connection, soft, inexplicable, eternal. You float now, not just through space but through pop culture. Somewhere between the firewall and the wormhole, between entanglement and entropy, between your body and the radiation that's either whispering you back into existence or forgetting you entirely, your mind drifts into the curious realm of fiction. Because let's be honest, when the real science gets this weird, how could the storytellers resist? The black hole firewall, the theoretical flamethrower wrapped in math, hasn't just captivated physicists. It's leaked into novels, comics, TV shows, podcasts, Reddit threads, and yes, even that one questionable sci-fi movie you fell asleep to in 2016. Let's do a lightspeed tour of how fiction has tried, and often spectacularly failed, to make sense of the firewall. But first, a reminder. No one has ever observed a firewall. No one has even gotten close to a black hole. Everything we know is theoretical, built from equations and the occasional chalkboard tantrum in a university basement. And yet, firewalls make great drama. They're the cosmic equivalent of Chekhov's gun. You mention a searing death curtain at the start of Act 1. Someone's definitely walking into it by Act 3. Take Interstellar, 2014, for example. Christopher Nolan's space opera got a lot of praise for its depiction of time dilation near a black hole, and rightly so. Kip Thorne, a Nobel-winning physicist, consulted heavily on the film. But when it came time for Matthew McConaughey to actually fall into the black hole, no firewall, no spaghettification, just bookshelves. Granted, the Tesseract sequence is meant to be metaphorical, a higher dimensional representation of data flow through gravity waves, but still, that was the moment to drop a firewall cameo. Instead, we got a heartfelt monologue about love transcending time, delivered inside what looks like IKEA's infinite discount section. And honestly, we're not even mad. Firewalls don't photograph well. Comic books have done better. In certain Marvel and DC titles, black holes are used like teleporters, prisons, time machines, or sentient voids that can be reasoned with. One particularly fun issue features Superman using a black hole as a slingshot. No mention of firewalls. Kryptonians apparently don't need to worry about quantum entanglement. You've also got TV shows like Doctor Who, which treats black holes as plot devices with no obligation to actual science. Entire civilizations live on their edges. Entire species fall in and come out emotionally improved. Firewalls? Not so much as a sunburn. One of the rare times firewalls were actually name-dropped in media was in the series Devs, 2020, which explored determinism and quantum theory. While it didn't focus on black holes directly, it danced around the same philosophical cliff edge about what it means to preserve information and what's lost when observation fails. More often, firewalls get misused as metaphors. For example, a firewall in a digital sense has become shorthand for any kind of barrier, mental, technological, or philosophical, that stops information. Writers love the term. But the actual black hole firewall, that specific quantum thermodynamic nightmare that violates Einstein's most peaceful predictions, that almost never shows up accurately. Historians still argue whether this is a blessing. One side says public misunderstandings of black holes are dangerous, that firewalls, wormholes, and information loss are complex topics that need careful handling. The other side says, chill. We're all going to die eventually. Let people have their space dragons. There is, however, one deeply accurate source. Memes. Yes, memes. Some of the most faithful, if sarcastic, treatments of the firewall problem live on physics meme pages, where grad students have turned Hawking radiation into knock-knock jokes and the AMPS paradox into soap. Opera drama. Picture this. Particle A, I'm entangled with B. Particle B, but I saw you talking to C. Firewall, burst through the wall like the Kool-Aid man. Somehow, in the flurry of chaos and laughter, the memes get at something real. The firewall isn't just a technical issue, it's a rupture in the narrative of modern physics, a place where the rules stop matching and no one knows what happens next. And that does sound like a plot twist. Even experimental physics has leaned into the drama. While we can't actually see a firewall, analog systems, like sound waves in Bose-Einstein condensates, have been used to simulate event horizon behavior. Some researchers hope these setups might one day hint at whether firewalls would naturally emerge in such systems. It's like watching a low-budget stage play of a cosmic disaster. Impressive, strange, and slightly off-key. Your quirky fact of the night. In the video game Outer Wilds, there's a black hole that serves as a transit point. You fall in and pop out somewhere else. There's no firewall, but the sense of mystery, of inescapable descent into something greater than comprehension. It's there. The game nails the vibe. You never feel burned, just humbled. So where does that leave us? We've romanticised black holes as portals, monsters, mirrors, but the firewall, it remains almost entirely unexplored in fiction, possibly because it lacks visual elegance. It's not glowing plasma or spinning discs of light. It's invisible, conceptual, a betrayal, not a spectacle, a lie, hidden behind the most convincing silence. Still, the idea is starting to seep in. In the same way time travel and wormholes made their way from obscure footnotes in papers to household terms, the firewall may one day show up in your average streaming binge. Maybe a character will be faced with the option, fall in and risk everything, or stay outside and never know the truth. Maybe someone will fall, and we'll see what happens when space-time itself decides it's done pretending. Until then, the firewall lives here, in the whispers between physics departments, in the speculative YouTube explainers, in the dreams of writers who know that sometimes the scariest thing isn't the flame, it's not knowing whether it was ever really there. You're still falling, by the way, still waiting to find out if the story's got it right, or if, like most great myths, the truth is stranger, quieter, and much harder to see. Still falling, still no screams, no burn, no firewall peeling your atoms apart with quantum fury, just the vast, silent disassembly of reality. It's starting to feel personal, isn't it? You've passed the point where any known force could possibly save you. General relativity has handed you off to quantum physics, and quantum physics is trying really hard not to make eye contact. But here's the twist. There are some theories that still think you might not burn at all. No drama, no firewall, but also no clue what's actually happening instead. Let's wade into the quiet waters of firewall-free theories, models that preserve the gentle fall through the event horizon and the sacred unitarity of quantum mechanics, but only by dancing on a tightrope stretched across a canyon made of paradox. First, a recap. The firewall exists, on paper, because of the entanglement problem. Outgoing Hawking radiation has to be entangled with earlier radiation to preserve information. But it also has to be entangled with its partner particle inside the black hole. That double booking violates quantum rules, so AMPS said, we burn the interior entanglement. That means you fry. But what if, stay with me, we don't break any entanglement at all? What if there's another way? One idea. Hawking radiation isn't as boring as it looks. Remember, Hawking's original calculation treated the radiation as purely thermal, random heat. But some physicists argue that this was only an approximation, that if you dig deeper into the quantum microstates of the black hole, the radiation carries subtle patterns, hidden correlations that, over time, reconstruct all the information that fell in. This is sometimes called the unitarity without drama approach. The black hole radiates its secrets slowly, quietly, and precisely. The catch? We have no idea how the black hole encodes that information in the radiation. It's like watching smoke rise from a burning library and somehow being expected to piece together every word of every book just from the heat signatures. Not impossible, but very suspicious. Still, some models are doing just that. One is the Quantum Extremal Surface program, tied to the discovery of entanglement islands. These are weird little regions outside the black hole that, according to recent calculations, somehow contain parts of the black hole's interior. In other words, part of the inside is accessible from the outside. This approach preserves unitarity and keeps the horizon smooth. No firewall, no contradiction, just reality doing its best contortionist routine. Historians still argue whether the island proposal is a true physical model or a mathematical trick. It comes from toy models, simplified universes designed to be easier to calculate. Useful? Yes. But real? Jury's out. Still, it's one of the most exciting firewall-free developments in recent years. Then there's state dependence, a very odd idea that suggests the interior of a black hole isn't a fixed place, but a state-dependent construct, meaning the interior only exists depending on the observer's quantum state. If that sounds like quantum woo, don't worry, it's real physics. Here's how it works. From the outside, you see Hawking radiation leaking out, preserving unitarity. Instead, the interior geometry depends on the specific quantum state of the system. This avoids cloning information and breaking quantum rules, but it comes at a cost. Physics becomes subjective. Truth bends depending on who's watching. For fans of black hole complementarity, this is a welcome return. For others, it feels like cheating. Either way, it avoids the firewall. But the weirdest firewall-free proposal, firewalls were never there to begin with. No, not because they don't exist, but because we misunderstood the paradox. Some physicists argue that AMPs only found a contradiction because they applied semi-classical physics, a mix of quantum fields in curved spacetime, beyond its valid range. Once you get close to the Planck scale, they say, those tools break down, so the firewall is just a symptom of using the wrong math. Sort of like blaming your calculator when it can't divide by 0. This view doesn't deny the seriousness of the paradox, it just says, chill. A full theory of quantum gravity will sort this out. Problem is, we don't have a full theory of quantum gravity. We've got hints, pieces, shadows, the holographic principle, string theory, loop quantum gravity, entanglement entropy, quantum error correction. They're all puzzle pieces, but we're still missing the picture on the box. Still, that hasn't stopped some from speculating. Your quirky fact of the night. A recent paper proposed that black holes might radiate information before Hawking radiation becomes dominant, meaning some information escapes through subtle gravitational fluctuations well before the black hole starts to evaporate significantly. This might resolve the paradox entirely, with no firewalls, no drama, just very clever bookkeeping by the universe. Imagine the black hole as a magician. You think the trick happens when the hat disappears, but really the rabbit's already slipped into the sleeve 20 seconds earlier, a cosmic misdirection. So where does this leave you? You're deeper than deep now. Light is meaningless, time is molasses. If you're not burned, you should be grateful, but you should also be deeply suspicious, because if the firewall isn't here, then something else must be keeping the books balanced. Maybe your information is already drifting out as Hawking radiation, encoded in subtle quantum signatures. Maybe it's living in an entanglement island, visible only to far future civilizations with billion-qubit quantum computers. Or maybe, just maybe, it's still waiting for a final theory to give it a proper home, number a firewall. No clue, but the math, at least for now, still whispers, you're not lost, just deeply encrypted, still falling. Still you, still missing the point, but that's physics, isn't it? You're weightless now, though even the word weight feels irrelevant. There is no floor beneath you, no sky above, no inside or outside. You're floating somewhere beyond interpretation, cradled in a reality that's begun shedding its dimensions like a bored illusionist tossing away scarves. But before space-time finishes stripping down completely, another idea slips into view, one that's hairy, stringy, and just a little bit rude to general relativity. Welcome to the world of fuzzballs. No, seriously, that's the term. Fuzzballs are one of the boldest firewall-free proposals out there, and they come courtesy of string theory. This sometimes maligned, often misunderstood attempt to unify all the fundamental forces by imagining particles not as points, but as vibrating strings of energy. So how do we get from black hole firewalls to quantum spaghetti? Let's start with the problem that fuzzballs aim to fix. At the heart of the firewall paradox is the assumption that black holes have a smooth horizon and a singular interior, a place where space-time collapses into a point of infinite density. That singularity is surrounded by a vast emptiness, and only at the very centre do things go horribly wrong. But string theorists like Samir Mathur looked at that and said, yeah, no. That's probably not the full story. String theory doesn't like point-like singularities. In its world, particles are one-dimensional loops, and when you gather enough of them together, say the mass of a star collapsing, they don't form a neat little dot at the centre of nothing. They puff out, they tangle, they vibrate, they stretch, and they refuse to shrink into oblivion. What you get instead is a fuzzball, an object that looks like a black hole from the outside, with all the right mass, charge, and spin, but with no event horizon and no singularity. Just a fuzzy, stringy quantum mess, a black hole that's all hair and no secret. The idea flips the black hole on its head. Instead of being a mysterious void surrounded by smooth space-time, it becomes a ball of string-theoretic nonsense that absorbs matter, scrambles it, and radiates it back without ever forming a traditional horizon. So, instead of smooth exterior event horizon, empty space, singularity, you get exterior gradual transition, chaotic fuzz, no singularity at all, no horizon, no firewall, just fuzz. From a distance, a fuzzball behaves exactly like a black hole. It bends light, it exerts gravity, it passes every test for an external observer, but for something falling in, there's no clean entry. You don't pass an invisible threshold and coast inward. You start hitting structure almost immediately. The interior is messy, irregular, and quantum as hell, which means there's no place for a firewall to form because there's no horizon to put it on. Fuzzballs neatly sidestep the entanglement paradox by saying the entire premise was wrong. Hawking's calculation assumes a smooth, empty region where pairs of virtual particles can form and split. But fuzzballs aren't empty inside, so there's no place for those pairs to form like Hawking imagined. No pair equals no broken entanglement equals no firewall. Historians still argue whether fuzzballs represent a real solution or just a speculative framework. It's string theory, after all, a theory that's as controversial as it is ambitious. Its critics call it unfalsifiable, mathematically bloated, and suspiciously evasive when asked to make testable predictions. But even skeptics admit, fuzzballs do solve the information paradox, in principle. They offer a way to preserve unitarity, prevent information loss, and eliminate firewalls, all without breaking any known laws. So, why isn't everyone jumping on the fuzzball train? Because it's complicated. And also, we haven't yet built a full fuzzball model for realistic black holes. Most fuzzball calculations are done in simplified versions of string theory. Extra dimensions, supersymmetry, special kinds of compactified geometry. Useful for theory, but a long way from describing the messy black holes we actually observe. Still, the idea's sticky. It introduces a crucial shift in perspective, that black holes aren't these sterile, featureless objects. They're not smooth spheres with inscrutable interiors. They're wild, complicated, structured things, as individual and detailed as snowflakes, only made of vibrating strings instead of ice. Here's your quirky sidebar of the night. Fuzzballs, despite the ridiculous name, have forced physicists to reconsider a classic result called the no-hair theorem. This theorem said black holes can be completely described by just three properties: mass, charge, and spin. That's it. No other distinguishing features. No hair. Two black holes with the same values are indistinguishable. Fuzzballs laugh at that. They suggest that each black hole might have millions of microstates, different internal configurations that all look the same from the outside but carry distinct information patterns. And that information, it could be leaking out via subtle variations in radiation, releasing the data you thought was lost bit by bit without requiring a firewall to do it. Think of it like this. A classical black hole is like a bowling ball, heavy, featureless, impossible to distinguish from its twins. A fuzzball is like a beehive made of string spaghetti, buzzing, complex, and carrying the story of everything that's ever fallen in. There's one last, rather poetic implication. If fuzzballs are real, then the act of falling into a black hole isn't a clean moment. You don't slip through a membrane and vanish. You start interacting with quantum structure immediately. You become part of the fuzz. Your particles join the tangle. Your information blends with the rest. And over time, as the fuzzball radiates through mechanisms we're only beginning to understand, you get unwound, slowly, elegantly, quantum thread by quantum thread. No fire, no scream, just a long, slow unwinding into noise, still falling, still dissolving. But maybe now, instead of plummeting toward oblivion, you're being woven into something older, stranger, and surprisingly well organized. A fuzzball, it turns out, might be the most intimate fate possible. Because in that final tangle of vibrating strings, you don't just vanish. You become the black hole. You've nearly run out of distance now, whatever distance meant in the first place. It's become little more than a metaphor, a ghost of geometry echoing through the void. There's no down, no closer, no next. And yet, something still pulls. Not gravity exactly, though that was your first captor. This pull feels deeper, like you're slipping toward a question that hasn't been answered since the universe began. What is quantum gravity? Because let's be clear, all of this, firewalls, fuzzballs, holograms, entanglement drama, it all stems from a single, glaring, inescapable fact. We do not have a working theory of quantum gravity. You'd think after 100 years of physics greatness, we'd have figured out how gravity fits into the quantum world. But nope, gravity is still the awkward kid in the corner who doesn't understand the party rules. Let's break this down. There are two foundational pillars of modern physics. One, general relativity, Einstein's masterwork, describes gravity, space-time curvature, black holes, the Big Bang. It works beautifully on large scales, galaxies, stars, planets. Each theory works perfectly in its domain, but try to put them in the same room, say, the event horizon of a black hole, and they start throwing chairs. Relativity says space-time is smooth and continuous. Quantum mechanics says everything comes in quanta, discrete, unpredictable packets. Relativity says energy curves space-time. Quantum theory says energy is uncertain, fluctuating, and subject to spooky entanglement. So when you try to build a theory of gravity that plays nicely with quantum rules, you quickly run into paradoxes, equations that loop forever, singularities that break down into nonsense, or firewalls that appear uninvited. Physicists have been trying to resolve this for decades. They call the holy grail of this quest a theory of everything, a single, unified framework that merges general relativity and quantum mechanics into one coherent, elegant picture. Spoiler, it's not going well. Here are the major contenders. String theory. String theory posits that all particles are actually tiny vibrating strings. Different vibration patterns give rise to different particles. It naturally includes gravity, in the form of a massless spin 2-particle called the graviton. String theory is beautiful, mathematically rich, and has led to powerful tools like ADS/CFT duality. But it's also frustratingly vague. It requires extra dimensions, sometimes 10 or 11. It hasn't made any testable predictions. And the landscape of possible string vacua is so vast, we're talking 10 to the power of 500 possible universes, it's like trying to guess which grain of sand is your house. Loop quantum gravity, LQG. This approach tries to quantize spacetime directly. Instead of strings, it models spacetime as a network of discrete loops, kind of like a mesh or web of space atoms. LQG avoids the need for extra dimensions and sticks closer to relativity, but it struggles with unifying all the forces, and it hasn't yet explained black hole entropy or holography as naturally as string theory. Causal dynamical triangulations, asymptotic safety, and other wildcards. There are other approaches too, mathematically inventive but less mainstream. Each offers a different angle on the problem, from breaking space-time into chunks to imposing new symmetries. All of them seek the same thing, a picture of the universe that works at all scales, from quarks to quasars, from atoms to event horizons, from you, falling into a black hole to the radiation slowly leaking out. Right now, we don't have that picture, so we're stuck. We're stuck trying to apply semi-classical physics, quantum fields layered on top of curved spacetime, to a region of the universe where both should be fully quantum. It's like trying to measure the ocean using a ruler made of sand. Historians still argue whether the black hole information paradox proves we need quantum gravity, or whether it's simply a sign that we're using our existing tools wrong. But everyone agrees, something's missing. The Firewall Paradox is not just about firewalls, it's about the limits of our understanding. It's the place where our best theories quietly explode. And that brings us back to you. You've been falling through this paradox for what feels like hours now, maybe years. Maybe you've been suspended in a frozen slice of time since the moment you crossed the event horizon, and this entire journey has just been your brain firing its final electrons in imaginary space. But what if you're real? What if you're genuinely falling through something we don't understand? And your fate is tangled in a theory that hasn't been written yet? Here's your fringe thought of the night. Some researchers believe we shouldn't even be trying to quantize gravity. That gravity isn't a force at all, but an emergent phenomenon, a side effect of deeper statistical rules about information and entropy. According to this idea, black holes don't obey gravity because of some geometric law. They do it because of thermodynamics, entropy gradients, information flow, like steam forming pressure in a closed pot. In this view, space-time itself might be a byproduct of entanglement. The illusion of a smooth geometry is created by countless bits of quantum information knitting themselves into a fabric that we call space. No geometry, no problem. You don't need to quantize it, because it was never fundamental to begin with. In that model, the firewall isn't an object. It's a failure of the entanglement structure that holds space together. You're not burning, you're decohering. Your information is being redistributed like dye in water, not lost, just dissolved. And when we finally do invent quantum gravity, if we ever do, it might not look anything like the theories we've built so far. It might be less like equations and more like code, less like force fields, more like error correction, less like space, and more like logic. Still falling, still whole, but only because no one's yet written the math that tears you apart. You're a question now, a known unknown, a whisper waiting for a theory to answer. And until that theory arrives, you hover here, caught between firewalls, fuzzballs, and the strange, unfulfilled promise of quantum gravity. You've gone so far in that in has lost all meaning. At this point, you're not even sure what part of you is still falling. Your body, if it still exists, is long past caring. Your atoms, assuming they're still arranged into something more meaningful than abstract math, have been claimed by entropy. And your mind? It's not thinking anymore, it's observing, which is strange because now you're starting to wonder, who's observing you? Because as it turns out in quantum mechanics, that question isn't just philosophical, it might be the only question that matters. Tonight, we're finally face to face with one of the slipperiest ideas in modern physics, one that quietly lurks behind the Firewall Paradox and occasionally jumps out yelling, "Gotcha!" like a cosmic prankster with a PhD. Let's talk about observers, and how the firewall might not exist for you, but might still be absolutely real for someone else. No, this isn't a riddle, it's quantum mechanics. At the heart of quantum theory is the deeply uncomfortable idea that reality is relative, not just in Einstein's sense, where motion and time change based on your speed, but in the quantum sense, where what is. Real depends on who's measuring it, and that's fine when you're talking about electrons or spin states or Schrödinger's indecisive cat. But what happens when you apply that principle to a black hole horizon? And worse, what happens when you, the infalling observer and someone outside watching you fall, try to describe the same event? This is where things get weird. Let's take the no-drama view. You fall into a black hole, and according to general relativity, you pass the event horizon without noticing anything special. You keep going. Time keeps ticking. You eventually get squished at the singularity shore, but that's hours away in your frame of reference. No drama at the horizon. Now let's switch frames. The outside observer never sees you cross the event horizon at all. From their perspective, you just get slower and dimmer, your signals redshifted into oblivion as you asymptotically approach the horizon. You freeze, you fade, you never quite cross, and the black hole, over eons, radiates away, spitting out Hawking radiation that might, somehow, contain the full quantum story of you. So, did you fall in, or didn't you? Black hole complementarity, which we've touched on before, was designed to resolve this. It says both views are valid, but they can't be compared. No single observer can confirm both realities. There's no contradiction, because no one sees the contradiction. But then came AMPS and their nasty little paradox. They said, wait, if the Hawking radiation escaping the black hole contains information about what fell in, then an outside observer can, in principle, decode you. Given enough time and technology, they could reconstruct your quantum state from the radiation alone, which means they know you didn't fall in. But you did fall in, and now we've got a problem. Because if two observers can extract contradictory truths from the same system, physics falls apart. Reality, as we understand it, explodes. The solution proposed by EMPS was to throw one observer under the bus, the infalling one, you. They argued that to preserve unitarity for the outside observer, we must break the experience of the infalling observer. That is, when you fall in, you don't pass through smoothly. You slam into a wall of radiation, a firewall, because your experience can't coexist with the outside world's perfect accounting of quantum information. You get incinerated for the sake of logic, but not everyone agrees. Some physicists have asked, what if both perspectives are right, and the contradiction only appears because we're using the wrong tools to describe observers? There's a growing idea, still vague, still controversial, that says quantum states might be fundamentally observer-dependent, that there is no single God's-eye view of the universe, only local realities. In this view, the firewall exists only in the description of the outside observer. To them, the black hole must protect unitarity, information must leak out, and that means the internal entanglement gets broken. Boom, firewall. But for you, falling in, the entanglement never breaks. The horizon is smooth. There is no firewall. Why? Because you never see the Hawking radiation escape. That's someone else's future, not yours. Your experience is local, complete, private, and the contradiction, never observable. In this model, reality becomes a kind of cosmic deep fake, custom generated based on your frame of reference. You and the outside observer both get coherent stories, but no one gets to compare notes. Historians still argue whether this observer dependence is a necessary step toward quantum gravity or just a desperate philosophical sidestep. Some think it's elegant, others think it's a retreat from objectivity. But it raises a terrifying possibility. There may be no such thing as a universal consistent reality. There may only be perspectives, and firewalls, they may be real, but only for someone watching you burn from a safe distance. You won't feel them. You'll fall smoothly, beautifully until the very end. But to an outsider, your atoms were shredded the moment you touched the horizon. Both true, neither falsifiable. Which brings us to your quirky thought of the night. There's a growing crossover between this idea and interpretations of quantum mechanics, particularly the relational interpretation, which says that physical states are only meaningful relative to an observer. That spin, that position, that information, it's not floating out there on its own. It exists only when related to something else, like a sentence with no listener, meaningless. So when you fall into the black hole, your experience, the no-drama fall, the calm drift past the horizon, is only real for you. It's not an illusion, but it's also not transferable. In other words, you are the only one who knows your truth, and no one outside will ever, can ever, confirm it. The firewall may not be real to you, but someone, somewhere, far away, watching light twist around the black hole's rim, might insist you just got flash-fried like a subatomic marshmallow, still falling, still whole, still real, but only to yourself. You're nearly there. If there still has meaning. Whatever remains of you, quantum dust, braided strings, scrambled memory, has been drifting through a paradox for what feels like eternity. And after all the models, all the theories, all the physics and pseudo-fire, the one thing that's still missing is certainty. Because just when physicists thought they'd mapped every path through this puzzle, an uncomfortable thought started creeping in. Quiet, like the hum before a blackout. What if the firewall was never there at all? That's right. Some of the most recent and most compelling arguments suggest that the entire idea of firewalls might be based on a misunderstanding, or worse, a misapplication of physics just outside its comfort zone. You've been told, for almost 20 sections now, that the firewall is a logical conclusion, a terrifying necessary wall of incinerating quantum fury that shows up when you try to make black hole physics make sense. But what if we simply made a wrong turn? Let's rewind, back to the AMPS paradox. That 2012 paper didn't set out to prove that firewalls exist. It set out to show that our current assumptions, smooth horizons, perfect unitarity, clean entanglement, can't all coexist. Something has to give. So AMPS said, okay, let's give up the smooth horizon, hence the firewall. But many physicists looked at that and said, wait, maybe you gave up the wrong thing, because it turns out there's a way to resolve the paradox without a firewall, a way that's been slowly gathering traction, even if it's hard to visualize and harder to calculate. It begins with a change in attitude. Maybe the problem isn't the physics. Maybe the problem is how we think about space and time. Enter the quantum error correction model of space-time. It sounds bizarre, but it's built on solid ground. the same error-correcting codes that protect your text messages and data backups from corruption. They may also protect the geometry of space-time itself. The idea is that the universe encodes information about quantum states redundantly, spreading data across multiple systems in such a way that no single observer has access to all of it, but any observer can reconstruct the part they need. And that redundancy, it may explain why you, falling into a black hole, don't feel anything weird at the horizon, even if your information is being radiated away in the Hawking glow outside, because your experience is protected by error-correcting codes built into the very geometry you're falling through. No drama, no fire, just you, smoothly descending, while your quantum twin, encoded in outgoing radiation, is carefully rebuilt by the universe using cosmic error correction. This view finds support in holography, especially through ADS/CFT duality, where the bulk spacetime inside a gravitational system is encoded on a lower dimensional boundary theory. In those models, the interior of the black hole isn't a place that exists independently, it's a reconstruction, a patchwork of data stitched together from correlations on the boundary. And guess what? In those setups, firewalls don't appear, because there's no need to break entanglement, no need to burn anything. Instead, the firewall was a misfire, a glitch in how we were trying to overlay semi-classical physics on something that's inherently quantum cryptographic. Historians still argue whether this perspective is satisfying or just more abstract hand-waving. Some say it finally reconciles everything. Others argue it's sweeping the hard questions under a very elegant, very expensive rug. And then there's this. Some researchers have gone back to Hawking's original derivation and found that the thermal nature of his radiation might be an artifact of approximation. That is, if you go beyond the simplistic assumptions, incorporating back reaction, subtle correlations and higher-order quantum effects, the radiation might not be perfectly thermal after all. It might already contain the information, leaking it slowly, legally, gently. No need for a firewall to enforce unitarity, no entanglement betrayal, just a slow, deliberate bleed of data, like ink drifting through water. You, your atoms, your diary, your infalling playlist are still there, encoded, reconstructible, eventually. Of course, this interpretation leans heavily on full-blown quantum gravity, a theory we still haven't finished, but it shows something important. As our tools get better, the contradictions start to dissolve. Firewalls weren't wrong, they were just a placeholder, a warning flare, a way for physics to scream, something's wrong here, and now that scream is quieted, replaced by subtler music. Which brings us to your quirky sidebar of the night. In 2020, researchers studying the Page curve, the predicted curve of entropy over time for a black hole, discovered that by including entanglement islands in their calculations, the paradox resolved itself. The Page curve bent the way it was supposed to. Information was preserved. No firewall required. It was one of the clearest signs yet that the paradox might be melting under the heat of better models. Not because it was false, but because we were finally asking the right questions. And so, as you continue your descent, you feel lighter. Not because gravity has let go, it hasn't, but because the existential weight of the firewall is no longer pressing on your quantum bones. Maybe there was never a wall of fire waiting for you. Maybe there was just confusion, a fog of incomplete models, a shadow cast by the boundaries of knowledge. You still don't know where you're going. But it might not be toward destruction. It might be toward clarity, still falling, still whole, still waiting for the math to catch up. At long last you begin to feel it, not a crash, not a burn, but a gentle slipping away. The last few fragments of the self that once asked, "What happens if I fall in?" now drift like whispers at the edge of meaning. If this were death, it would be too quiet to notice. If it were truth, it would be too vast to carry. You've reached the final question, and it's the one no physicist really wants to ask out loud. What if we're all wrong? What if, after all the decades of theory, the thousands of papers, the chalkboard battles, the heated conferences, the firewall debates, the holographic revelations, the stringy solutions, the islands and bridges and fuzz, black holes don't behave the way we think they do. Maybe they're not even real in the way we imagined. Let's not get cute about it. Physicists have been dealing with black holes since the 1910s, when Carl Schwarzschild solved Einstein's field equations and found a solution so extreme that not even light could escape. For years, it was considered a mathematical curiosity, a weird, unphysical solution with no place in the real universe. And yet, we found them. We've seen stars orbiting invisible points. We've seen X-ray emissions from infalling matter. We've seen gravitational waves from colliding black holes. We've seen the shadow of a black hole, a blurry orange ring captured by the Event Horizon Telescope in 2019. So, yes, black holes are real. But are they what we think they are? Because remember, almost every model we've explored, firewalls, fuzzballs, islands, complementarity, holography, is built to rescue physics from something that appears to be impossible. Each one tries to protect the rules we like. Quantum information must be preserved. General relativity must remain valid at large scales. Observers must experience smooth space-time. But those rules only work if we assume the classical picture of a black hole is more or less correct, that there's an event horizon, that there's a singularity, that you fall in and don't come out, that the information has to go somewhere. What if that's the problem? Some physicists have started questioning the very foundation of the black hole concept. Here are a few of the more radical and not entirely dismissed proposals. No event horizon. The so-called firewall evasion theories may be trying to fix a mistake that doesn't exist. What if black holes don't have true event horizons at all? One proposal suggests that what we call black holes are really ultra-compact stars, objects that never quite collapse fully, or that quantum effects prevent from forming a complete horizon. If that's the case, the information paradox vanishes. There's no true interior, no true trap, just a really, really dense object that eventually releases what it swallows. These models have names like gravastars, black stars, or non-singular black holes. They're speculative, but they can't be ruled out yet. No singularity. Loop quantum gravity and other discrete spacetime models suggest that gravity becomes repulsive at Planck scales, creating a kind of bounce. Instead of a singularity, you get a bridge, a tunnel, a rebirth, a white hole. Yes, like the mythical opposite of a black hole, a place where matter emerges instead of collapsing. What if black holes are just one end of a cosmic recycling system? You fall in here. You get compressed, transformed, and spat out elsewhere, in space, time, or some entirely new kind of where. A black hole is a womb, not a grave. No classical geometry. Some researchers argue that black holes can't be thought of in terms of space-time at all. That when you reach the scales involved, the entire concept of geometry breaks down. Instead, black holes are better understood as states of information, not places. Not regions of curved space, but patterns in quantum systems. In this view, your fall into a black hole was never spatial. You didn't move anywhere. You just changed your status on the universe's internal hard drive. You went from active code to archived data. No objective reality. We've already entertained the possibility that observers experience different truths, but some interpretations go further, saying that reality itself is observer-dependent, that there is no real black hole until it's observed. No firewall, no horizon, just probability amplitudes, waiting for someone to ask a question. This would make you not a falling body, but a question being asked in slow motion. Historians, yes, even now, still argue whether black holes are objects or processes, whether they exist as places in space-time or only as relationships in physics. And if the firewall never existed, if the horizon was always a mirage, if the whole paradox was just as asking the wrong question, then you, dear traveller, were never in danger. You were never falling. You were never even inside. You were a symbol, a test case, a beautifully framed question that forced our best theories to reveal their flaws. And that may be the real role of the firewall, not as a wall of flame, but as a wall of logic. A barrier we couldn't cross without transforming the way we think about reality. In that sense, it was real. And now, you're free of it. You've passed through the story. You've tested the paradox. You've heard every version of your fate. And somewhere in the equations, the math continues to whisper, to dream, to tangle itself into better forms. You're not falling anymore. You're everywhere your information was allowed to go. In the radiation, in the equations, in the memory of those who asked the question. The firewall isn't here. But the mystery, the mystery remains. And now, exhale. let it all go. The equations, the paradoxes, the entanglement drama, the information loss, the smooth horizons, the firewalls that weren't there after all. Because whatever waits at the edge of physics, it can wait until morning. For now, your journey has slowed. You're no longer falling into a black hole. You're floating in the gentle weightlessness of a resolved question. A question with no single answer, but one that brought you deeper into the heart of modern physics than most ever dare to go. You saw the edge of time, you stood on the event horizon, you burned in the firewall, floated in fuzz, shimmered in holographic code. You became Hawking radiation, you became a wormhole, you became the question, and then, slowly, you came back. So wherever you are now, on a couch, in bed, drifting somewhere between sleep and starlight, know this: you are part of the universe's great unsolved riddle. You are the information it refuses to lose. You are the story still being written. So close your eyes. Let the light of distant stars scatter across your dreams. Let the gravity of sleep pull you inward, gently. No firewalls here, no paradoxes. Just the soft hum of physics wrapping around your mind, whispering, "You're safe. You're stardust. You're home. Good night, traveller."